quantum mechanical model is a quantitative approach, but it demands high computational facilities. There is another way to find out the transition probability without using the equations of quantum mechanics. This is the group theory approach. By using the concepts of group theory, we can predict whether a particular transition is allowed or not. This is quite logical because each orbital and dipole moment has a particular symmetry. And fundamentally, it is the symmetry that allow or forbid a transition. In group theory, to find out the transition probability, instead of integrating the product of wave functions, we use symmetry labels. As we know, each orbital or wave function and dipole moment operator has a symmetry and can be represented by an irreducible representation. We have already discussed how to find the irreducible representation using the character table of the point group. Suppose the HOMO is under the irreducible representation tau I. The LUMO is under tau F and the dipole operator comes under tau mu, which may be a combination of different irreducible representations depending on the molecular symmetry. If we want to determine the all possible interactions between the three, we will have to determine their tensor product, which is this. Suppose our tau I is A1, tau F is B2, and tau mu is A1 plus B1 plus B2, then their tensor product will be this. Then, the tensor product will contains B2 plus A2 plus A1. If the irreducible representations of the final state, operator, and initial state have dimensions 2, 3, and 3 respectively, their tensor product forms an 18-dimensional reducible representation. Each symmetry operation in this representation is represented by an 18 by 18 matrix, and the character of the identity operation is therefore 18. This reducible representation can be decomposed into irreducible representations using the standard reduction formula, ensuring that the total dimension of all irreducible components equals 18. Now group theory says, if the tensor product contains at least totally symmetric representation, that is A1G or A1, then the transition is allowed. If not, then the transition will be forbidden. The physical meaning is, in an electronic excitation, light's electric field tries to excite electron density from HOMO to the LUMO. If symmetry allows a net dipole oscillation, light couples to the molecule, absorption occurs. If symmetry forces cancellations, no absorption takes place, hence no transition would be observed.